Hello, standing waves in a string or wire. So let's just recap the origin of standing waves. Here we have two waves travelling in opposite directions that have the same frequency and amplitude, and what we get is a regular pattern of constructive and destructive interference for the particles in the medium. And so this particle in the medium is always getting destructive interference, and so it would be a node, whereas this particle is always getting constructive interference and is getting supercrests and supertroughs, so that's an antinode. Alright, and so what we're going to do is just introduce a bit of terminology here. So this would be what's referred to as our fundamental frequency. This is the simplest standing wave you can have, where you have a node and an antinode in between. And in this case, the wavelength of the standing wave, if we were to look at it, and let's make it pretty colour, if we were to look at it, a full wave, let's make it bigger, actually let's make it quite big. The full wave is going like this, and then comes down here, and underneath me, hopefully that's not in the wave, so we have our crest and our trough, and so this, if this length here is L, that's the length of the standing wave is 2L. Got that? Now if we were to draw the next one, and the next one we have is the next possible standing wave for this length of string, and we must have a node at both ends, and so the next one up from this one has one node, and so between each node you must have an antinode. So there's an antinode there and an antinode there. Now if I drew this one, if I drew the wavelength of this standing wave, it is this, and so the wavelength of this standing wave is L. Now here we have the next one, so if we've got one node, the next variation or vibration in this string would have two nodes, so that we have a node there and a node there. Let's draw that node, and between each node we must have an antinode, antinode, and antinode, and so they progress. And again, if we were to draw the wavelength for this one, this is where we get the fractions from. That's the wavelength, and we can see that wavelength is 2/3 of L. Does that make sense? Right. Now, this is called the fundamental frequency. This is the second frequency and the third frequency at which you get a resonance. In between these frequencies, you don't get a standing wave, and we'll demonstrate that as well. Now, this is taken it a step further. And so you can see that we get progressively more and more standing waves and more nodes and antinodes. Let's move on. Now, some terminology. The most basic one is called the fundamental, and we've done that, and using the universal wave equation and the subscript 0 representing the fundamental, we can say that F equals V on the wavelength. V is the velocity within this string. And so the fundamental frequency would be V on 2L. Now the next one is referred to as the second harmonic, because this is the first harmonic, and harmonic really is meaning what is a resonance. So this is the first resonance, so it's the first harmonic. This would be the next one that occurs. So if we, from here to here, we're increasing the frequency, and we get a whole lot of chaotic patterns. But then when we reach this frequency here, we would get this pattern here, and so this is the next harmonic, the second harmonic. It's also referred to, just to confuse you, as the first overtone. That has its origins in music, and so some people get confused by that. First overtone but second harmonic, and this is the formula for it. Now L's one wavelength, and the frequency of this will be B2V on 2L. Now the next one is the third harmonic, or the second overtone, and the frequency of this will be 3V on 2L. Okay, and you can generally work that out. You don't have to memorize that if you understand it. Now this equation, because we're talking about a stretched string, sometimes we're just given enough information, we have to use this equation, just enough information to use this equation on our information sheet, which is hidden away there. And this one is v equals the square root of t on what's that, u micro lambda something, I've forgotten, sorry. So v is the velocity of the wave in the string or wire, t would be the tension which you would be given in newtons, and this is the unit density. And the unit density, the only thing you have to worry about the unit density is sometimes you have to work it out, and they don't give you the formula for unit density, but the unit density is just the mass in kilograms divided by the length in meters, and that's what you have to. So sometimes you have to use this to work out the velocity, and then they usually ask you some other questions, but it's only once in a blue moon that they do. Now in the next section we'll look at standing waves in air columns, which are similar but different to standing waves in stretched strings. See ya.